Okay, the second talk of this session is local conflict coloring. Papers by Pierre Fregnault, Mark Heinrich, and Adrian Kosowski. And the talk is going to be given by Mark.
Thank you very much. So, does it work? So I'm going to talk about distributed algorithm and in particular some graph coloring problem in the distributed setting. So first I'm going to introduce you the local model. So for those who listened to the previous talk, it will be a bit repetitive. So in this model we have a set of processes, n processes, and these processes are modeled by the nodes of a graph. And each processor can only communicate with its neighbors in the graph. An algorithm in this model will proceed in a sequence of rounds, and at each round, all the nodes will send a message to their neighbors, receive all the messages from their neighbors, and then perform some local computations. So at the start of the algorithm, each processor is given some local input. So the processor doesn't have access to So at the beginning of the algorithm, the processor do not have access to the whole input, but only a small part of it. And after a certain number of rounds, they have to give some local outputs such that all the outputs taken together give a solution to the problem. So additionally, we suppose that we do not have a bound on the size of the messages that can be sent in one round, and there is also no bound on the computation power of the nodes. Also, at the beginning, the nodes have identifiers which are simply integers written in log n bits. So the first two assumptions are really unrealistic assumptions. The reason we study this model is that we try to look at the locality of a problem, meaning at which distance do you need to communicate in order to solve the problem. So the problems which are studied in this problem are what we call locally checkable languages. So it's problems for which we can check a solution in a constant number of rounds. So by checking, I mean that there is an algorithm that if the solution is correct, all the nodes will output yes, and if it's not correct, at least one of the nodes will output no. So two examples of such problems are delta plus one coloring and maximal independence set. So for both these problems, the input of the problem is actually the communication graph formed by the processors and their neighbors. So here is a summary of the results that are known for these two problems. So these two problems are widely studied in this model. So what we can wonder from this table is, for example, is delta plus one coloring easier than MIS? So we can see that we have slightly better algorithm for delta plus one coloring than for MIS. For example, we have delta to 3/4 plus log-star instead of delta plus log-star n, and so on. And actually, the answer to this question is yes in the randomized setting because of this lower bound here and of the algorithm on the top right. However, in the deterministic setting, this question is still open. Another interesting question is the complexity of delta plus one coloring. So we can see that the best deterministic algorithm for delta plus one coloring is only exponential of square root of log n, while the best lower bound is only log star n. So log star is the number of times you need to iterate the log function to get a number smaller than 1. So it's a function that grows really, really slowly. We can get closer to this lower bound either by allowing randomization, so allowing the processes to draw random bits and to fail with very small probability. Or we can also add delta, so the maximum degree of the graph, in the complexity of the algorithm And in this case, we have for coloring an algorithm that runs in delta to the 3/4 plus log star n. Okay, so this is for the model. So our contribution in this model is a new way to formulate problems in this model that we call conflict coloring. So what is conflict coloring? A conflict coloring problem, the input to the problem is a list of colors for every node. And on each edge, there is a list of conflicting pair of colors, which are forbidden colors for this edge. And at the end of the algorithm, we must produce a coloring such that each edge chooses a color in its list, and there is no edge which is colored with a pair of colors from its list. So, for example, here we have two nodes. This is not a good solution because the pair 1, 2 is in the conflict list of the edge, and 1, 4 is a good solution because it's not. So for this problem, we will look in particular at two parameters. So the first parameter is the parameter L, which is the size of the list. And intuitively, if your lists are larger, the problem should be easier to solve because the nodes can choose from have more choices, so they're less likely to have conflicts with their neighbors. On the other end, there is the other parameter that we look at is what we call the conflict parameter, D, which is the maximum number of times a color appears in one of the conflict lists of an edge. So this parameter quantifies the amount of conflicts that we have between two neighbors. And intuitively, the more conflicts you have, the more difficult the problem will be to solve because one color will potentially have conflicts with many others. And in the following, we will look at actually at the ratio L over D. And the higher this ratio is, the easier the problem should be. So why is this problem interesting? So this problem is interesting because actually any local problem can be encoded as a conflict coloring problem. So a very simple example for coloring, we can use, to formulate it as a conflict coloring, simply use the initial colors. So all the nodes have the same list. And since we don't want to get monochromatic edges at the end, so we put on as conflict all pairs of the form CC for every color C. And with this formulation, the conflict parameter D is equal to 1, and the ratio L over D is simply the number of colors. So a second example, a bit more complicated, is for a maximal independence set. So here in the formulation, the colors will have the form 0, 1, or 0i, or 1i. So if a node is colored 1i, it means that it will be taken in the corresponding MIS, and none of its neighbors will be in the MIS. If it's colored 0i, then it means that it's not in the MIS, but its if neighbor is in the MIS. And the conflicts between these colors will be simply conflicts when we have colors which correspond to incompatible assignments. So for example, colors 1i and colors 1j will be in conflicts because they try to put two adjacent nodes in the MIS. There is also a conflict if we take two nodes U and V is the if neighbor of U. There will be a conflict between 1i and 0j because color 1i say that V is in the MIS and color 0j says that V is not. And with this formulation, the ratio L over D is only 2, so it's much smaller than for coloring. And actually, we can show that this is the best we can do for MIS. So this can be a hint as to why MIS is more complicated than coloring even in the deterministic setting. Okay, so the main results of our papers are the two following algorithms. So if the ratio L over D is large enough, then we have algorithm to solve this problem. So the first algorithm says that if L over D is larger than delta square log delta, we have an algorithm that runs in time log star n. A special case of this first algorithm is the problem of delta square log delta least scoring, so we can solve in log star n time, and there were no previous results known for this problem. The second algorithm works if L over D is strictly larger than delta. And in this case, we have an algorithm which runs in square root of delta plus log star n. And the special case of this second algorithm is the problem of delta plus 1 coloring. So we can solve it in time square root of delta plus log star n, which is better than the previous known algorithm, which was only delta to the 3/4 plus log star n. Actually, the second algorithm is based on, so it was Barenboim's algorithm, and it simply reuses the same ideas of the algorithm and replaces part of this algorithm with the first one. So I'm only going to give more details on how the first algorithm works, which is the next part of this talk. So how does it work? So the main idea of the algorithm is so we have this problem that we want to solve, so conflict coloring with L over D greater than delta square log delta. And we call P0 this problem, and from P0 we are going to build a second problem, P1, with a ratio L over D which is greater. And we are going to continue like this until we get a problem PT with a ratio L over D, which is sufficiently large so that we can actually compute a solution relatively easily. And from this solution PT, we are going to build the solution to all the problems that we build sequentially until we get solution S0 to the problem, to the initial problem. So actually, any of the arrows here will be performed in one communication round. So the runtime of the algorithm will be simply the length of this sequence of problems. Okay, so before I give more details on how this algorithm works, I'd like to explain another algorithm, which is this one. So it's Lineal's algorithm, which computes a delta square coloring of a graph in times log star n. So why do I want to explain this algorithm? Because actually our algorithm can be seen as a generalization of this algorithm, except that we have a ratio L over D of delta square log delta, and here it uses only delta square colors, so we lose a log delta factor. So actually this algorithm can be seen with the same can be seen as having more or less the same general idea, except that we will build a sequence of coloring problems, and actually we don't need to communicate to build problem pi plus 1 from problem pi. So this sequence of problem in the original paper is done, building this sequence of problem is done implicitly, and we can only see, and we can see this algorithm as a color reduction technique. So when we have enough color, computing a coloring is easy. You can simply use the identifiers of the node. Okay, so how does this algorithm work? So suppose that we have problem pi, so we have a certain set of color C. The problem pi plus 1, in the problem pi plus 1, the new colors will be subsets of colors of problem pi. And it won't be just any subsets. It's so the new set of colors will be a set family. So family of subsets such that any two subsets in the family have a small intersection. So why do we put this? Why do we need this assumption? Is actually to compute a solution of problem pi from a solution to problem pi plus 1. So suppose we have a solution to problem pi plus 1, so every node has chosen a subset of colors that is different from its neighbor. Now we want to compute a solution to problem Pi, so vertex U is simply going to choose a color in its set, but it doesn't want this color to be chosen by any of its neighbors. So it's simply going to remove from set SU all the possible colors which are in SV for any of its neighbors V. And because of the condition that we have that any two different subsets have a small intersection, we know that there is at least one color in this set here. And actually, we can build such family of subsets such that this set of colors C prime is exponentially larger than C. So by doing this, we can actually reduce the number of colors to get a delta square log delta coloring. And in Lineal's algorithm, there is a final step to get to delta square coloring that we were actually not able to adapt in our algorithm, which is why we only get delta square log delta. Okay, so how does it work for conflict coloring? So now we have in our problem Pi, each node has a list of colors, and we have some conflicts and a certain ratio L over D. Now we follow what is done in Lineal's algorithm and take as new colors all possible subsets of colors of a certain size. And now we want to be able to compute a solution to problem Pi from a solution to problem Pi plus 1, so we add some conflicts between subsets which intuitively have too many conflicts. So what do I mean by that? Suppose we have a solution to problem Pi plus 1. So every vertex has chosen a color SU, and this color SU is not conflicting with any of the colors of its neighbors. So vertex U wants to compute a solution to problem Pi, so it's going to choose a color in SU, and it's simply going to remove from SU any of the colors which is conflicting with one of the colors in SV. And because of the condition that we put, we are sure that there is at least one such color. And so if we do this, hopefully optimally, if we take all possible subsets like this and we define conflicts between subsets, we get conflicts which is not too high. Actually, it's not exactly what we get, but what we get is that on average, subsets won't have too many conflicts. So by removing only a small number of subsets, or at most a constant fraction, we can control the conflict parameter is a new problem, and we get a ratio L over D, which is also exponentially larger than the ratio L over D for the previous problem. So that's essentially how the algorithm works. So as a conclusion, I showed you a new formulation for local problem that we call conflict coloring, and I presented one algorithm for this problem, and we have another one. And so what can be interesting to look at is to look at if there are other problems which can be expressed as conflict coloring problem. So we've seen that it works pretty well for coloring. It works also for list coloring. It doesn't work well for MIS, but if we can look at maybe the other problem. So the complexity of delta plus 1 coloring is still a long-standing open problem in the area. And finally, we can try to compare the complexity of MIS delta plus 1 coloring and delta plus 1 list coloring. So the first two is resolved in the randomized setting and is open in the deterministic setting. And so from what we've seen in our work, it seems that delta plus 1 list coloring isn't much harder than delta plus 1 coloring, although it's still open. So thank you.